back, and for this lecture we're going to be talking about atmospheric stability. So if you haven't watched the previous lecture yet on adiabatic cooling, make sure you go back and do it. But just for a super quick review, what I really want you to know is as air rises, it cools adiabatically. What that means is that it cools at a temperature independent of the surrounding atmosphere. And this is because it doesn't exchange heat with the surrounding atmosphere. As a result, it cools at its own rate. Now, there are two types of adiabatic cooling. There's dry adiabatic cooling. This occurs when the air inside the parcel is unsaturated. Therefore, it cools at a rate of 10 degrees Celsius per every 1,000 meters. And then there's moist adiabatic cooling. In this case, the parcel is saturated, some latent heat is being released, that slows down the rate of cooling. In this case, the parcel cools at a rate of 6 degrees Celsius per every 1,000 meters. Now, with that said, why do we even care about any of that stuff? Well, we care about it because it determines whether a parcel is able to rise or sink. And that is this concept of atmospheric stability. So before we begin, let me ask a pretty obvious question. Suppose you have a ball, and you have it in the middle of a valley, and so surrounding the ball are hills. When that ball is at rest, it's in a situation called equilibrium. Now think of another ball, a ball on top of a hill in this case. And on every side of the ball, it's downhill. But in this position, the ball is also at rest, also in equilibrium. Now think about what were to happen if you pushed those two balls. If you were to push the one in the valley, push it out of its equilibrium, it would roll up one into the hill and then slide right back down to the bottom of the valley. In this case, when you pushed it away from its equilibrium, it eventually returned back to its equilibrium. That is what's called stable equilibrium. On the other hand, if you have the ball on top of the hill, if you nudge it in any direction, you remove it from its equilibrium, it's going to continue to roll down the hill. In both cases, gravity is acting on the parcel, or gravity's acting on the ball, sorry. Gravity's acting on the ball, causing it to either return to its original position or move farther away from it. So, in the case of a stable equilibrium, taking the ball, pushing it up the hill, results in it rolling back down. In an unstable equilibrium, the ball is at rest at the top of the hill. If you accidentally nudge it in either direction, it just rolls down and keeps rolling down. You don't have control over it. So, in a stable situation, the ball returns to its original position. In an unstable situation, the ball moves further away from its initial position. Now, in the atmosphere, stability determines whether air rises or sinks. So think about the ball again. In a stable atmosphere, if you have air at the surface and you push it up in the atmosphere, it just sinks right back down. In this case, that air can't escape the surface of the earth. It can't travel up into the sky. In a situation like this, if you have any clouds, they're going to be very low clouds, and they're going to be very spread out. On the other hand, in an unstable situation, if we have a bubble of air, one of these parcels, and we were to throw it up in the atmosphere, it'll continue to rise, and continue to rise, and continue to rise, eventually condensing and creating a cloud. So we care about stability because it greatly determines weather conditions at a location. When you have stable air, you have something that looks kind of like this. You have these very thin, very low clouds that hang out near the surface of the earth. And they can't rise higher into the atmosphere. So the air above them is usually very clear. So in this case, you have a lot of air that hangs out near the surface and can't escape. Now think about this though. This isn't just for clouds. This can also be for things such as pollution. In a stable atmosphere, pollution has a really hard time escaping, and so it can just stay put and build and grow, and pollution can become worse and worse and worse. Certain instances such as the Denora smog crisis or the Great London Smog event or any other events like that have been caused by extremely stable air. Now, in the case of unstable air, air from the surface of the earth is allowed to rise very high, and eventually it reaches the tropopause where it spreads out. Now, if this air is very unstable and it's able to rise really quickly, it can even move beyond the tropopause into the stratosphere, creating what's called an overshooting top. This is an example of very unstable air. Air from the surface is able to just shoot up really fast. So, what actually determines stability in the atmosphere? Well, what determines stability in the atmosphere actually doesn't really have much to do with the air parcels themselves. Rather, it has to do with the atmosphere, the ambient environment. Now I'm talking about the atmosphere outside of the parcel. So, suppose we have our parcel. Suppose we have our parcel right here. So here's our parcel. So suppose we have our parcel. Everything outside of the parcel is what we call the ambient environment. So it's everything outside of the parcel. And so when we talk about the ambient environment, we're talking about the air outside of the parcel. And remember, this air outside of the parcel is doing its own thing. It's not cooling adiabatically like the parcel is. So with that said, the parcel is isolated from the ambient environment. And therefore, the parcel itself is only cooling adiabatically. The ambient environment, on the other hand, is completely different. The air surrounding the parcel cools at a different rate. Things such as radiation, advection, certain winds, all have impacts on the ambient environment. Therefore, the temperature of the ambient environment is almost always different than the temperature of the parcel. So the temperature of the outside atmosphere is different than the temperature of the parcel. Now, how do we actually determine the temperature of the ambient environment? Well, this is where weather balloons come in, and this is where those STUV diagrams that I had you guys drawing a few modules ago, this is where all of that comes in. In the case of measuring the ambient environment, you take a weather balloon, you tie an instrument pack down here. Actually, the instrument pack's over here, sorry. You take that instrument pack, you tie it to the balloon, and you launch it into the atmosphere. As it gets launched into the atmosphere, it takes recordings of the temperature of the ambient environment. We can then plot those results on something called a sounding. Now, this sounding is a little bit different from the one that you're used to using with the STUV diagram. This one is something called a skew-T log P. And you don't have to really use that this class, so don't worry too much about it. But what it shows you is it shows you how air temperature, that's this black line on the right, how it changes with height. Whenever you see it decreasing like this, that means it's getting colder with height. Whenever you see it traveling to the left to the right like this, that's increasing with height. So we can look at these to determine the ambient temperature of the atmosphere. Now with that said, we now have the parcel, which cools adiabatically, and the surrounding environment, which cools at its own rate. It cools at its own way. It's completely different than the parcel. Now, we need to compare these two temperatures. We need to compare the temperature of the air parcel to the temperature of the ambient environment. Since air parcels are adiabatic, they don't exchange heat with the environment. They don't exchange heat with the environment. Therefore, they are not, almost always, never the same temperature as the environment. They're usually either warmer or colder than the environment. And this determines whether the parcel is able to rise or sink. If the air parcel is warmer than the environment, it's buoyant. This means that it can continue to rise. Since it's warmer, it's less dense. Since it's less dense, it rises. On the other hand, if the parcel is colder than the surrounding environment, it sinks until it's at the same temperature as the environment. So in this case, in the case where the parcel is warmer than the environment, it rises. If it's cooler, it sinks. So if it's warmer, it rises. If it's cooler, it sinks. And we can determine the stability of the atmosphere based on this. The atmosphere is stable if when a parcel of air is pushed upward, the parcel is cooler than the ambient environment. In this case, if we take the parcel and we push it upwards, it just sinks right back down. On the other hand, the atmosphere is unstable if it is warmer than the ambient environment. In this case, the parcel will rise. So it'll sink if it's cooler than the ambient environment. It'll rise if it's warmer than the ambient environment. And the way that we can compare these two is we can actually take a look at a sounding on a STUV diagram like the ones that you've been doing, and we can actually plot the temperature of the atmosphere and plot the temperature of the parcel. Remember, the temperature of the atmosphere is going to cool based on a million things, so we need a weather balloon to measure it. The temperature of the parcel, however, is going to cool adiabatically, so we can just do that ourselves. And then we just compare the two temperatures. Wherever the parcel is warmer, the atmosphere is unstable. Wherever the parcel is cooler, the atmosphere is stable. In a stable atmosphere, the ambient atmosphere is warm. As a result, the parcel is cooler. This occurs either where an inversion is present. In this case, the parcel still cools with height, but the atmosphere is actually warming with height. So inversions are a good example of a stable atmosphere. Or in any location where the atmosphere doesn't really cool much with height. In this case, the atmosphere stays warm while the parcel is cooling. In a stable atmosphere, air can't rise. In this case, you get very thin, low stratiform clouds. Clouds like cirrostratus, altostratus, and stratus clouds. Clouds that are thin and layered. So here's an example of a stable atmosphere. Here in the middle, this represents the temperature of the environment. And as you can see, it's only cooling at a rate of 4 degrees Celsius per every 1,000 meters. In this case, both dry parcels and moist parcels are going to be colder than it. So they're going to have to sink. In the case of a stable atmosphere, you have warm air on top of cold air. Warm air on top of cold air is stable. So warm air on top of cold air. And a stable atmosphere can also look like this. Near the surface of the Earth, you have very cold air, and any pollution that's in that air stays trapped. Meanwhile, above the surface, you can have warmer air. Since this air down here is cooler, it can't rise. Therefore, it just stays trapped, and you get this pollution. So if you ever look outside on a sunny day and you see a brown layer near the surface of the Earth, that's because it's a very stable atmosphere, likely due to an inversion where the temperature of the atmosphere is warming with height. Now, unstable atmospheres are a little more tricky. And the reason why they're a little more tricky is because we have dry parcels and moist parcels. Remember, dry parcels cool faster than moist parcels. A dry parcel cools at a rate of 10 degrees Celsius per every 1,000 meters, while a moist parcel cools at a rate of 6 degrees Celsius per every 1,000 meters. As a result, if the temperature of the atmosphere cools slower than a dry parcel, but faster than a moist parcel, we get an interesting situation where dry parcels can't rise, but moist parcels can. And so this gives us two types of stability. The first type is called absolute instability. In the case of an absolutely unstable atmosphere, the atmosphere cools faster than the dry adiabatic lapse rate. So in this case, the atmosphere is cooling faster than 10 degrees Celsius per every 1,000 meters. And in this case, any air parcel will continue to rise. If you take a parcel of air and you push it up, it will continue to rise. So this is an absolutely unstable atmosphere. However, in a case where the atmosphere cools slower than the dry adiabatic moist rate, but faster than the moist rate, you have a situation where unsaturated parcels will stay cool. They will stay cooler than the surrounding environment and they can't rise. However, if the parcel is saturated, that allows it to rise. So in the case of a conditionally unstable atmosphere, only saturated air parcels can rise. And in this case, the atmosphere's lapse rate is in between the dry and the moist rates. An absolutely unstable atmosphere is pretty common, and it usually doesn't give us a lot of interesting weather. It occurs when ambient temperatures decrease rapidly with height. So if the ground is very, very warm, such as during the daytime, and in fact, the air is very stable very unstable during the daytime, this allows air to rise really easily. Other things such as advection can also greatly influence an unstable atmosphere. In an unstable atmosphere, in an absolutely unstable atmosphere, any parcel can rise. In this case, the environmental lapse rate is greater than the dry rate. As a result, both dry, and moist parcels can rise. In this case, you have cold air on top of warm air. And this is a very unstable atmosphere. Now, with all of this said, moisture ends up becoming a pretty important thing in the atmosphere. And as a result, well, even if you have heat, if you don't have moisture, you don't really get a lot of interesting weather. So all the stuff we're going to be talking about in a few weeks, things such as hurricanes, severe thunderstorm outbreaks, tornadoes, none of that would happen if you didn't have moisture. With that said, this whole adiabatic cooling thing actually gets a little more complicated. So, in the last lecture I talked about dry air parcels and moist air parcels, but that's not the common case. Normally what happens is you have a parcel at the surface that's unsaturated, meaning it's warmer than the dew point. However, as the parcel rises, remember, the air temperature in that parcel begins to decrease. Eventually, it can reach the dew point. If it reaches the dew point, which of these three things are going to happen to the parcel? If it reaches the dew point, this means the parcel becomes saturated. In this case, the parcel becomes saturated. What's going to happen to the parcel? Will it suddenly stop rising and begin to sink? Will it cool but dry adiabatically, still cool dry adiabatically? Or will it cool moist adiabatically? Take a moment and think about it. Well, the answer is the parcel begins to cool moist adiabatically. Why? Because now moisture is condensing, latent heat is rising, or latent heat is being released. Therefore, it began rising dry adiabatically, but then it cooled to the dew point, began to condense, and began to rise moist adiabatically. We actually call the height that this happens the lifted condensation level. As a parcel rises, it cools until it reaches the dew point. Once it reaches the dew point, moisture condenses, clouds form, and the parcel continues to rise, but now it cools moist adiabatically. And this is what's called the lifted condensation level. The elevation where all of this begins is called the lifted condensation level. Now, the lifted condensation level is actually really easy to identify. All you have to look for is 1, where does the parcel cool to the dew point? And 2, where is the base of a cloud? The base of the clouds is the lifted condensation level. Everywhere below that, the parcel was too dry and too warm to condense. At that cloud height, at that base, that is where the parcel cooled enough. Now, with that said, in a conditionally unstable atmosphere, you have a situation where the atmosphere cools at a rate slower than the dry adiabatic lapse rate, but faster than the moist adiabatic lapse rate. In this case, dry parcel sink, but moist parcel rises. And therefore, moisture is actually a pretty key ingredient. We'll talk more about that in a few weeks. But here is a time when this happens. If you have a parcel of air at the surface and it's unsaturated, and you allow it to rise, it eventually will cool to the dew point. Once it cools to the dew point, condensation begins, a cloud forms, and the parcel continues to rise moist adiabatically. Now, look at this though. The environmental lapse rate cooled quicker than a moist parcel, but slower than a dry parcel. In this case, near the surface of the Earth, the environment was warmer than the parcel. Therefore, the parcel was cooler than the environment, meaning it would be stuck down here. It wouldn't be able to rise too high. However, as soon as the parcel begins to condense, it quickly becomes warmer than the surrounding environment, and it's able to continue to rise. Now, this is going to be very important in a few lectures when we begin to talk about thunderstorm formation. But for now, just know that as a parcel rises, it cools. If it reaches the dew point temperature, it also begins to condense, and you switch over from the dry rate to the moist rate. Here's a quick review of everything we talked about today. As air rises, it cools. The rate of cooling depends on if the parcel is saturated or not. If it's unsaturated, it cools at a rate of 10 degrees Celsius per every 1,000 meters. If it is saturated, it cools at a rate of 6 degrees per every 1,000 meters. The atmosphere is stable if the parcel is cooler than the environment, forcing it to sink. It's unstable if it's warmer than the environment, allowing it to rise. And then the type of instability depends on how quickly the atmosphere cools with elevation. In a stable atmosphere, the atmosphere cools slower than the moist rate. In a conditionally unstable atmosphere, it cools at a rate between the moist rate and the dry rate. And in an absolutely unstable atmosphere, it cools at a rate faster than the dry rate. That's it for today. Next time we're going to talk about how these parcels of air can even get pushed above the surface. And that'll be a pretty quick talk. Until then, I'm Terrence Mullen.